Hi there, my name is Pablo Barros and I'm here to present our paper named CIAO, a contrastive adaptation mechanism for facial expression recognition. I'm working on facial expression recognition for a while now, in particular with convolutional-based representation learning. And one of the most important characteristics of these models is their ability to learn general patterns from images. In the case of facial expression recognition, that is great for one side. Humans are able to perform several facial expressions. And given that our facial structure does not change much from person to person, there are patterns within these facial expressions that are recurrent in several different persons and become easily depicted and learned by convolutional-based learning. On the other hand, the interpretation of these expressions might not be as general as their representation. One person could express a smile and yet want to convey a negative affective cue. The particularities of how each person expresses emotions are usually lost and difficult to be depicted by representation learning methods when trained for general expression recognition. The power of personalization is usually addressed with expensive and, in most cases, unpractical solutions. One of the problems of balancing generalized and personalized face expression representations comes from convolutional-based representation itself. Usually, conv-nets are trained in a supervised manner and require or a large amount of samples or using expensive transfer techniques to bypass the learning of basic image structures that might compose a face. Most of the popular and usually most successful facial expression recognition methods are trained for extreme generalization. Facial samples are clustered around a known affective concept, and the convolutional filters of a neural network are tuned to find and highlight specific patterns that are common for each of these affective concepts. Usually, these networks are trained with what is known as in-the-wild datasets, the most prolific, containing millions of images separated in a set of categorical or continuous emotional concepts composed of arousal and avoidance values. In these cases, these neural networks have two very important characteristics. The facial representation is done by looking at specific patterns that are repeated in the training data. And second, these patterns are highlighted by the convolutional channel in respect to the label these models are trained on. The first characteristic is easier to understand, given that we are treating facial expression recognition as a computer vision problem. Healthy faces, independent of the persons, have the same facial structures. These structures move in a similar manner, forming expressions. So much that the facial action units can actually be perceived in different persons and encoded by experts to form clusters of facial positions. Conv-nets are known to depict these structures, given that they are present when training the convolutional layers. Given a large enough sample, the less convolutional filters are observed to encode to learn the encoding positions of eyes, mouth, chin, cheeks, eyebrows, for example. Even on unsupervised or self-supervised neural networks, the facial structures are learned only if they are present on the training and test set of a dataset. This, of course, leads to the understanding of a universality argument that persons from different cultural backgrounds can characterize and understand the set of basic emotions these datasets were trained on. Again, this reflects directly on how these datasets that we use were composed and designed, and thus how we build and evaluate them, and which scenarios we deploy our automatic perception models. The problem is that this was usually not enough to provide an universal emotion perception model. Deploying a model in a robot, for example, usually did not produce a good performance, or when used in real-world demos, it did not achieve the same 90% accuracy it had achieved on a certain dataset which was evaluated with. Of course, we started looking into this from a model performance perspective. Maybe we did not have enough samples. Maybe the data was not very varied enough. Maybe the model could not learn, did not have the best learning function or whatever. But only recently, the entire concept of universal emotions started to be seriously questioned. Recent work shows that although there exists concepts and facial expression characteristics that are universal, their understanding changes drastically from scenario to scenario. The entire concept of emotions as something which is not monotonic definition is very well spread, but its definition is a concept that is created by the individual, making the individual perception and understanding of affect a norm, instead of the generalized universal concept is rather new. The impact of these findings have on our computational models is huge, especially on its application and adaptation towards different scenarios. In this paper, we present then a facial expression adaptation model that adapts convolutional learned representation of facial expressions based on known concepts of other affective scenarios. Our model is built in a way that facial expressions and their representations within the neural networks are easily deformed to form new representations that are useful for other scenarios. Our model, CIAO, is based on a contrastive adaptation of the last convolution layers from facial expression encoders. In reality, it learns a specific deformation of the high-level facial representation based on the labels from other affective scenarios. To achieve this deformation, CIAO relies on effective facial representation, and in this paper we investigate two of them: the face channel, that learns facial representations in a supervised manner, and the prior knowledge network, referenced here as PK in the slides, that learns in a self-supervised model, using a generative adversarial network to represent facial expressions. In order to evaluate the capability of these models to learn facial representations and to investigate their limitations, we train them using different datasets. Each of these datasets has specific characteristics. The AffectNet dataset is used as our baseline model, and it has more than 1 million labeled samples crawled from the internet. The FER dataset contains grayscale images annotated by the same set of evaluators. The FER Plus dataset reannotates the same images from FER using a crowdsourcing methodology, providing a different understanding, effective understanding from these images. The JAF dataset is a traditional computer vision scenario that has only 213 images from 10 different persons collected in the 1990s, while the EmoReact dataset has images only from children obtained from a single YouTube channel, and is the only one in this list that has labels associated to short videos and not static images. For each of these datasets, one different decision-making architecture is attached to them that allows it to train and evaluate each of the encoders in a specific manner for each of these datasets, which in return allows achieving the best performance for each dataset, which is what we're interested in investigating here. To evaluate the capability of the face channel and of the prior knowledge network to learn facial representations, but also their capability to adapt towards different scenarios, we train them first with the AffectNet dataset that allows them to have a full facial expression representation that consists of learning from a range of 1 million images. We then proceed with 3 experimental setups. First, we retrain the entire encoders with each of the other datasets. This allows us to verify the capability of the encoders to learn the effective representation of that dataset by first learning the effective representation of the AffectNet dataset. On the second experimental setup, we train only the last convolutional layer of the encoders, which usually contains a high-level facial representation. This way, we adapt this high-level representation towards the ones found in each of the datasets. In the third and last evaluation, we train only the decision-making layers, using the facial representations learned from the 1 million images of the AffectNet dataset, a traditional transfer learning scenario. All these 3 scenarios are used to evaluate these models, both performance-wise, but also their capability of transfer learning within them. As expected, retraining the entire network achieved the best result for both encoders. We are changing the entire structure of facial representation, from the low-level features learned by the very early convolutional channels of these networks, of these facial encoders, to the high-level ones, which represent the facial representation modulated by the effective information coming from the labels of each of these datasets, together with the decision-making layer. When training only the decision-making layer, that means we are reusing the facial representation which is learned from the AffectNet dataset. This showed to be problematic for the JAF and EmoReact datasets. These datasets have much different samples from the usual representations learned from the AffectNet, but also in specifically case of the JAF dataset, it does not have enough samples to train such a complex neural network. Training the last convolutional layer together with the decision-making layer provided a good balance between a high effort of retraining the entire encoder and the low performance obtained when retraining the decision-making layer only. That means that we don't retrain all the layers of the network, but only the last one, only adapting the high-level facial expression representation towards that affective computing, that affective scenario. This produces a performance which is in between the first and the full training and decision-making training. With these results, we established that these encoders can learn different facial representations and affective concepts from these datasets in a very effective manner only when retraining the entire network. But this is expensive, as we need to retrain all the layers of this network counting encoder and decision-making layers for every new scenario. Also, this makes the facial encoder completely adapted to one specific scenario, making it very difficult to be reused in other scenarios without extensive retraining. In this regard, we propose here in this paper CIAO as a plugin layer. It consists of an inhibitory convolutional layer that is attached to the last convolutional layer of the facial encoder. It is trained based on the dataset's label, using a contrastive loss, which allows for a fast adaptation of these layers. The inhibitory convolutional filter acts as a deformation of the last convolutional layer of the facial encoder, but does not change the original structure of the facial encoder, neither the learned representation of the facial encoder. That means that the CIAO layer plugin learns its own way of how to change the original encoder's facial representation towards the affective representation of a new dataset. We can quickly train one plugin for each dataset. The original face encoder can be reused as many times as we need, because the original facial encoder will not change. What changes is just CIAO. And because CIAO is just one convolutional layer, it's very fast and very cheap to train and readapt. We evaluate the impact of CIAO in the same three settings we originally evaluated the facial encoders. In all cases, the performance gain with CIAO is significant, in particular when training only the decision-making layer without changing the facial encoder representation at all. In this case, CIAO improved drastically the performance even on smaller datasets as JAF, or very unique datasets with very unique facial expression and affective representation, as the ones found in the ImoReact dataset. If we look to the facial representation alone after the application of CIAO, we understand that it learns to focus this representation, this deformation, on the important characteristics of each of these datasets. So a plugin trained for the FER dataset will learn very specific characteristics that only exist on the FER dataset, which are not transferable for the JAF dataset, and vice versa. In this case, training CIAO also happens in a much faster and computationally cheaper manner than retraining the entire network. So besides gaining performance, you will also gain efficiency on this training this plugin. In conclusion, our contrastive inhibitory plugin was able to create a generalization of affective perception by modulating the affective concepts towards specific scenarios in a very fast and efficient manner. This allows the interpretation of the generalization of facial expression recognition to be connected to adaptability, instead of focusing on fixed and predefined affective concepts. Well, and with that, I finished my presentation. In the links you are seeing in the slide, you can directly contact me if you have any specific question or if you want to discuss any possible collaborations. I'm up for any of this. You also can find all the implementation details about the models that I presented here, specifically CIAO and the encoders, but also other models we are working on regarding face expression recognition. I am, of course, available for questions if there are any. Thank you very, very much. It was a very nice experience to be here.